Hello and welcome back again. We are now in section 1.3 of chapter 1. This is a difficult and lengthy section, so I will split it into 3 videos at least. And in this video, I will cover the notions of open subsets and closed subsets of R. Now, a subset of R, O, is said to be open if it satisfies a certain condition. Okay, it's a property. What does this condition state? It states that for every point in O, I can find a neighborhood, if you like, or a small interval around that point, totally contained in O. This is a condition. Not all subsets satisfy this property. So what I'm going to do now is to give examples and counterexamples of open sets. Okay? Okay, I said this. So examples. The interval 0, 1 without its endpoints is an open subset of R. Now, why I didn't say the open interval? Because there may be a confusion here. Because when I say the open interval 0, 1 is open, it may seem something very strange to you, because it would sound like a tautology. It's like I'm saying x equals x or a implies a, but it's not. Because in open, there is a difference between the use of the word open or the adjective open in both. So when I say open interval, by definition, the open interval 0, 1 is the set of numbers between 0, 1 without 0 and 1. But an open subset of R is a set that satisfies this property, this condition that I stated here. So I need to prove that this set 0, 1 satisfies this property. Okay. Now this is not difficult, by the way. It's very easy. So let us start with a picture. So consider an element x in 0, 1. So a number strictly between 0 and 1. So it is at a positive distance from 0 and at a positive distance from 1. So this is my x. Can I find a neighborhood of x, an interval around x, totally contained in 0, 1? Of course. The interval in red satisfies such an interval, but it's not unique. I can find a bigger one. And the bigger one, what if I go to the biggest one? This is what usually mathematicians love to do, to take the biggest such. What is the biggest such interval that I pictured in red here? Well, it seems that the radius of the interval here, it's x. So it's x minus x, x plus x. So it'd be something of the form x to x. But there's a problem. So we would say that 0 to x is contained in 0, 1, which is not true for all x. It's true if x is less than 1/2. But if x is bigger than 1/2, then we have to take a smaller interval. So you see what is the radius of the biggest interval that you must take? It should be what? It should be either the half of the interval, the r, if you like, should be x if x less than 1/2, or 1 minus x if x is bigger than 1/2. Okay, so we have to take the minimum between the two, and this is what we will do. So take now, if x is positive, so the minimum of x and 1 minus x is what? Is either x if x is less than 1/2, or 1 minus x if x is bigger than 1/2. Yeah, and this is something positive because both numbers are strictly positive. And now I claim that this interval x minus r, x plus r is totally contained in 0, 1. Okay, and this is not difficult because how do I prove that? I take an element here and prove that it's here. So take y in x minus r, x plus r in the red interval, if you like, that I drew before. Then what does it mean? So it means that y, first of all, y is less strictly than x plus r. And now r is less or equal than minus x. Okay? So x plus r is less or equal than x plus 1 minus x. And this is just 1. And y is strictly less than x plus r, which is at most 1. So y is less than 1, strictly. This first thing. And similarly, if y is in this interval, it's strictly bigger than x minus r. So since r is less or equal than x because it's the minimum, okay? So r is both less than or equal than x and less or equal than minus x. If r is less or equal than x, then minus r is bigger or equal than x. So I get x minus x, which is 0, and therefore y is strictly positive. So it belongs to 0, 1, and that's it. So I proved that the interval 0, 1 with endpoints excluded satisfies the property or the condition of openness. Okay? And the same reasoning that I use in this case applies to any interval of the form AB with endpoints excluded. Okay, just replace 0 by A and 1 by B. Okay, so I suggest that you rewrite the proof in this case. It's exactly the same. So what you should have to take here, you have to take, so you take x between A and B. What do you have to take here? We have to take R, the minimum between x minus A and B minus x. And then you repeat the reasoning here. Okay, I'll not do it, you do it to test your understanding. So any interval of the form AB without its endpoints satisfies the condition or the property of openness, of being open. And the reasoning that we used also applies of intervals of the form of or unbounded intervals, A plus infinity. In this case, you don't need to take the minimum. Just in this case, we take R to be x minus A, right? If x is here. Try to write the proof. So this set is open according to our definition of open, and similarly for this one. And now the proof is easier than in this case of 0. Okay. The empty set is open. Why? Because the openness condition is a condition. It tells, what does it say? It says that if whenever you have a point in the set, you have an interval around the set. Okay, but the empty set has no points, has no elements. So the condition is trivially satisfied or vacuously satisfied. So the open set, the empty set is an open set. And the whole line R is also an open set because everything is in R here. Any interval is in R. So you can take any R actually in the definition. So the first conclusion is that all open intervals are open sets. And once again, this is not a tautology. I'm proving something. Now, this is not difficult what I'm proving, but it's not totally trivial. Okay, so open intervals are open sets. Okay, and hence the terminology open. This is why we call them open. Okay. Now, but there are open sets that are not intervals. Okay, so all open intervals are open sets, but the converse is not true. For example, R star, which is R without 0, is also an open set. The proof is easy. How do we prove that? We take an arbitrary element in R star, and you have to find a number R such that x minus R, x plus R is contained in R star. Now, the easiest thing to do is to distinguish between two cases, because if x is in R star, then either x is always positive, or then either x is positive or x is negative. If x is positive, simply take R equal x. Then of course R is positive, and the interval x minus R, x plus R is just the interval 0 to x, open. And this is of course in R star because it doesn't contain 0. And by symmetry, if x is negative, you take R equal minus x. Then R is positive, and x minus R, x plus R, the interval, is the interval 2x 0 without 0. And so it's also contained in R star. Actually, I can combine the two cases in one case by just taking R equal absolute value of x. Okay? So R star is an open subset of R. Okay? It satisfies the condition of openness. Now, another example of an open set which is not an interval is the set R without Z, which is the set of real numbers which are not integers. Okay? I claim that this set is open. Why? How do I prove that? There are at least two ways of proving this. I will give you one of them. I go back to the definition. So I take an element x in R without Z. So x is not an integer. But I know that x has a floor number, and I call this number n. I know that x, by definition of the floor function, is between n and n plus 1. But since it's not an integer, it's strictly between n and n plus 1. Okay, so it cannot be equal to n, cannot be equal to n plus 1. Now, we already observed that n plus 1 is an open set. It's an open interval. Okay, so I can find, and x is in that interval. So x is in the interval n plus 1, and this interval is open. So I can find a smaller interval around x contained in n plus 1. And there is a formula for R. I gave it to you, actually. If you want a formula for R, it would be the minimum between x minus n and n plus 1 minus x, if you like. But this is not important. You can take any number less than that. Now, okay, between n and n plus 1, there's no integers. Okay? So if there are no integers here in this interval, there are no integers here in the smaller one. So what does this mean? It means that this small interval is contained in R without Z. Okay, both are contained. The bigger one is contained in R without Z because if an element is here, it cannot be an integer. So it's necessarily here. And so the smaller one is also in R without Z. And that's it. I prove that R without Z satisfies the condition or the property of being open. Okay. And for a completely similar reason, R without N, which is a bigger set actually now than R without Z, is also an open set. Try to prove it using a similar idea of here that we used here. Okay, I will not do it, but same thing. Just test your understanding by writing down the proof. Now, an arbitrary union of open sets is also an open set. I suggest that you also prove this to test your understanding. Start, if you like, with just two sets, A and B. A open, B and B open. Prove that A union B is open and see what happens. Okay, but you can take any union actually. So try to prove that. So the union of two open sets is an open set. And a finite intersection of open sets is an open set. Now, here, note the difference between arbitrary and finite. Okay, you can prove easily this. Start with proving these in the case of just two sets. It's enough to prove this for two sets because then you can use induction on the number of. But it's not true that an arbitrary intersection of open sets is an open set. And I'll give you an example. Try to give a counter example. Actually, it's not true. So we cannot say that an arbitrary intersection of open sets is an open set, but a finite intersection of open sets is an open set. Try to prove that. Now, examples of non-open sets: the interval 0, 1, open at 0 and closed at 1, is not open. Why? Because if you take x equal 1, no matter how r is small, the interval 1 minus r, 1 plus r, cannot be contained in 0, 1 because of the numbers between 1 and 1 plus r exceeds 1. So this interval, so no matter how r is small, this red interval is 1 minus r, 1 plus r, cannot be contained in 0, 1. Okay, so the interval 0, 1, semi-open, if you like, is not open. Not because it's closed. It's not closed either, actually. Okay? And I will get to close that later. But this set does not satisfy the condition that I gave in the definition. Does not satisfy the openness condition. And for a similar reason, no singleton can be open in R. Why? Because a singleton cannot contain an interval of the form A minus R, A plus R, unless R is 0. But in my definition, R is positive. So one-point sets or singletons cannot be open. Also, the set of rational numbers, Q, cannot be open. Why? Because it cannot contain an interval. Because any interval is contained contains rational numbers and irrational numbers. So since it contains irrational numbers, it cannot be totally contained in Q. So Q cannot contain any interval, and therefore it cannot be open. Same thing for the irrational numbers, because any interval contains rational numbers, so it cannot be contained in the irrationals. Okay, so all these sets are not open. Also, the integers, the non-negative, the natural integers and the relative integers are also not open, because I cannot find this, because they contain no intervals. Okay, same reason. So openness is a condition. It's a property that a set may possess or not. Okay. Now, I talked about neighborhood, but in an intuitive sense. Now, but we have a precise definition of neighborhood. What is a neighborhood of a point? A neighborhood of a point is just a set that contains an open set that contains the points. Okay. And now I'll give examples. Usually, we denote the set of neighborhoods by this calligraphic Q of X. And okay, so this set of neighborhoods is never empty, because R, the whole line, is always a neighborhood of all its points. Okay, because it's open. So I want to show what is a neighborhood. So an open set containing a point is a neighborhood of that point. But in this definition, a neighborhood need not be open. Okay. So for example, if the closed interval -1, 1, let us say, is an open neighborhood, is a neighborhood of 0, let us say, or a neighborhood of 1/2. And more generally, it's a neighborhood of all points strictly inside. But -1, 1, first of all, it's not a neighborhood of 1 and -1. Okay, we saw that why. Okay. So now I have to attract your attention to the fact that there is another definition of neighborhood that you might find in books. So there's no agreement between mathematicians. Some mathematicians define a neighborhood by just being an open set containing a point, simply. Okay. So according to them, this -1, 1 is not a neighborhood of 0, let us say. In our definition, a neighborhood need not be open, but it contains an open set containing that. Okay. Now, in practice, it makes a little difference. There is a little difference between the two, because we can always assume that the neighborhood that we take is open. If it's not open, we take a smaller one. Okay. And according to our definition, any set containing a neighborhood of X is itself a neighborhood of X. Okay. Now we move to the notion of interior of a set. The interior of a set is the biggest open set contained in the set. It's usually denoted by a circle, sometimes by int A. And the elements of a circle are called the interior points of A. And now I'll give examples. What is the interior of the closed interval 0, 1? 0, 1 with boundary included, with endpoints included. Of course, many of them will think that it's the open interval 0, 1. And this is indeed the case. Why? How do I prove this? Well, first of all, 0, 1 open is open, right? We proved that. And it's contained in 0, 1. But the interior of 0, 1 is the biggest open set contained in. So what does it mean? It means that this set is contained in the interior, right? Because this is the biggest one. And both are contained in 0, 1 closed. So I have a set, I don't know what is it now for the moment, but it's a set between these two, between 0, 1 open and 0, 1 closed. What are the possible cases? There are just 4 cases. This intermediate set is either this one, or 0, or yeah. So what are this? Okay, so let me write this. So there are 4 possibilities, because there are just 4 sets between these two extremes. Either 0, 1 open, or 0, 1 semi-closed, or so closed at 1, or closed at 0, or 0, 1. Okay, these are the only possibilities. But which one of these 4 is open? This is not open, right? This is not open. This is not open. This is the only open set. So what does it mean? It means that the interior of 0, 1 is necessarily this one. Okay, and this is the result. This is a simple proof that corresponds to our intuition that the interior of the interval, of any interval actually, is just the interval without the endpoints. Okay, so this is as a rule. And now the reasoning that we used also proves that the interior of 0, 1 semi-closed, or closed at 0 and closed at 1 is the same thing. So same reason. So this corresponds to our intuition. Now, less trivial is the fact that the interior of Q, of the rational numbers, is empty. Why? Because the only open subset, the only open subset of Q is the empty set. There are no open. No. If Q had a non-trivial open set, then it would contain an interval. But there is no interval in Q. So the only open subset of Q is the empty set, and therefore the biggest one is the empty set. So we say that Q has an empty interior. And for a similar, so for a similar reason, the interior of the irrational numbers is also empty, because the irrationals cannot contain any non-trivial interval. Okay. And same thing for the integers Z. The interior of Z is also empty. The interior of N is also empty. Same thing. Okay. Now I move to closed sets. Or maybe I will stop the video here, because maybe it's too much information for. So I think it's better to split the video into 4 parts. So I will stop now and continue in the next video.